In this ICFD++ example, we're going to demonstrate a 2D ball falling into water using the new Integral Computational Multiphysics Advanced User Interface, or ICMP AUI. Before diving into this example, I will briefly cover the new features and components of the ICFD++ AUI for the first-time user. For more in-depth understanding of the ICMP AUI features, common across all Metacom software, please click on the ICMP AUI demo link popping up on the left side of the video, or refer to the ICMP AUI section of your ICFD++ documentation. This ICFD++ interface is composed of the menu bar, where the mouse is currently moving, the toolbar, which has the shortcuts to the commonly used functions and visualization controls, the canvas, in which a geometry or solution is displayed, and the notebook, currently showing that you are in a CFD++ simulation. Within the notebook, ICFD++ has its action tree, or setup wizard, which will guide you logically through the various steps of the problem setup, and one or more information trees. In this case, a groups tree and a boundary families tree and a boundary conditions tree. Corresponding to each action item in the action tree is its action panel, where the user is given the relevant choices based upon choices made in previous and current panels. All panels are dockable and resizable. Before selecting the working directory for this example, we are going to concatenate two grids contained within subdirectories. The concatenation tool can be accessed by going into the menu bar, Tools pull-down menu, the Grid Files Manipulation menu, Create New Topology from Existing submenu, Concatenate submenu, and Using Subdirectories submenu. This will bring up the Concatenation Tool by Subdirectories panel. Since we have two subdirectories containing grids, we are going to create two subdirectories in this subdirectory tree. We will press on the plus button twice. We will highlight the first subdirectory with a single left mouse click while also checking it. We will select the Browse button and double click on the back subdirectory. This will contain the grids for our background grid. Once this has been selected, we will press Open at the bottom. Next, we will highlight the second subdirectory with a single left mouse click, while also checking it. We'll once again enter the Browse window, and this time double click on the Ball subdirectory. This subdirectory contains the grid for our overset ball grid. We'll press Open again to accept this. Now back in the Concatenation tool panel, we will select Run in the tool runner, and once the concatenation has completed, a question will be prompted of whether or not we want to run the grid analysis tool. We will say yes. Then it will ask us whether or not we want to create an egroupsin.bin file. This file will allow us to visualize the different groups in our concatenated grid. We will say yes to this as well. Then we are prompted with grid information regarding our concatenated grid. You'll notice that we have all quadrilateral cells, since this is a 2D grid, and we have 6 external boundary families. We will confirm this by pressing OK at the bottom. We will say yes to the prompt of whether or not to redisplay the grid boundaries. And then we will dismiss this panel. Now we will proceed with the setup wizard. The first item in our action tree is selecting a working directory. We will choose the default working directory and press OK at the bottom to proceed. We are prompted with whether or not we want to load the egroupsin.bin file that's been found in our current working directory. We will say yes to this option. Then we're in the Load Input Grid Info action item. Here we will say OK at the bottom. We are then prompted with the grid information. We will accept this and press OK and proceed. Then in the Cell Types and Volumes action panel, we are told that we have only quadrilateral cell elements, and this is taken from the grid analysis. We will say OK to proceed. In the General Problem Definition action item, we will choose General Fluid Problems as the type of problem we want to solve. Once this is selected, we will say OK at the bottom to proceed. In the CFD Problem Definition action panel, the fluid type we will say is multiple phases, since we have both gaseous air and liquid water. Are the fluids miscible? We will say no. We will say yes to it being a viscous flow, and we will also say yes for it being a turbulent flow. We are not interested in solving for energy transport in this problem, so we will select no to this option. And the simulation type will be transient. Once this has been set, we will say OK at the bottom to proceed. In the additional specifications action panel, we will be applying a grid motion, so we will say yes to that option. We will not be activating a 6-stop based motion, so we'll keep that as no. We will be activating a prescribed motion, so we will say yes to activate other types of motion. Since this is an overset grid, we will be doing cell cutting and blanking, so we'll say yes to this option. We will not be using the expert AUI interface for cutting, so we'll keep that unchecked. All other options can be kept at their default no state. We can proceed by pressing OK at the bottom of this panel. Next, we are taken to the cutting and blanking controls panel. Here, we want to add 2 ranks, so we will highlight the ranks tree and single left mouse click the plus button twice. Before proceeding with the cutting and blanking controls, I want to point out some basic mouse controls in the canvas. With your mouse cursor in the canvas, we can zoom in and out by holding down the right mouse button and moving the mouse up and down. We can translate by holding down the middle mouse button and moving the mouse around. And we can also rotate using the left mouse button. Since this is a 2D grid, we want to stay in the XY plane. So we can go up now to the shortcut button row and select Fit XY. And we'll revert back to our default XY view. We can also toggle the 2D grid on and off by clicking on Toggle 2D. Now if we zoom in, we can see the overlap of cells with this overset grid. Now the goal in this cutting and blanking controls action panel is to first remove the background grid contained within the overset grid while still retaining some amount of overlap. The overlap will be at the zonal of the overset grid. That is the goal of the first rank. The goal of the second rank will be to minimize the overlap. Now we can proceed to specifying the first cell cutting rank. We can highlight this using the left mouse button. The first thing we'll do is identify the cutter boundaries. So for this first rank, we will highlight and check cutter BC's families _1, identifying that these will be the cutters for the first rank. We are going to use boundary family number 5, the zonal of the overset ball, as our cutter. So we are going to mark cut cells in the background grid using this cutter boundary. The group we're going to blank will be the background grid. In order to identify the group number, we can expand the groups tree in the notebook, and by single left mouse clicking one of the groups, we can identify which cells belong to which group. Now we'll notice that the background grid belongs to group 1, and since those are the cells that we want to blank in this first rank, we will check that group. Now we need to identify the live boundaries that we will be marching from. So we want to march from all of these outer boundaries towards this zonal cutter boundary. So we will select left, right, bottom, and top as our live boundaries. Now going back to the first option here, since we are using a zonal boundary as our cutter, we do want a small overlap. So we will retain cut cells here to create that overlap. So we will keep that at the default yes. Once this is set, we will then go to rank number 2. We will once again retain the cut cells to create an overlap. The objective of this rank is to minimize that overlap using a technique that is called supersequential cutting. Here, we will use the boundary faces created by the blanking in rank number 1, BC 7 and 8. So these have already automatically been created after setting up the first rank. And we're going to be blanking out the overset grid, so group number 2. And since we're blanking out the overset grid, we want to set a live boundary that's part of the overset grid family. And in this case, it'll be the ball boundary. So we're going to march from the ball boundary towards this overlap region. And once again, the purpose of this rank is just to minimize that overlap that was created from the blanking in rank number 1. So once this is set, we can press OK at the bottom to confirm and proceed. In the equation properties action panel, we will be solving this as a RAN simulation. We will be using the 2-equation realizable K epsilon turbulence model, and we will not be solving any passive scalars. So once this is set, we can press OK to proceed. In the physics source terms action panel, we will say no to the option to adding a physics source term. You can press OK to proceed. In the reference quantities action panel, we will be solving this in dimensional mode using SI units. In the fluid properties panel, we will be applying properties for both the gaseous and liquid phases. The tracked phase we want to specify as water. So we can scroll down the liquid database tree and select water with a single left mouse click. And then we will drag and drop this into the tracked phase tree for fluid properties _1. We'll hold down the left mouse button and drag and drop. So now the properties of water have been added to the tracked phase. Next, we're going to apply air as the gaseous phase into the fluid properties for the hidden phase. So we will expand the gas list, highlight air with a single left mouse click, and drag and drop into the fluid properties for the hidden phase. We will apply a base pressure of 1 atmosphere, 101,325 pascals. The bulk temperature we will keep at 288 Kelvin. No surface tension effects will be applied, but we will turn on buoyancy. We will not recalculate bulk density. For the dimensional gravity components, we will apply minus 9.81 meters per second in the y direction. The gravity reference point we will set to be at a y location of 0.15. Typically for the gravity reference point, we want to choose a location that's part of the lighter phase, which in this case is the air. And we want to also make sure that it's away from the interface between the two phases. The bulk density we will set as the lighter phase, and we will set to 1.225 kilograms per meters cubed. Now, since this is a closed domain, pressure is not anchored by any boundary condition. In these types of simulations, we want to anchor the pressure, so we can expand the advanced settings and say yes to turning on pressure anchoring. We are prompted with a message saying that by activating pressure anchoring, the multigrid agglomeration has been set to 5 groups. This is a recommended value in cases with this activated, so we will say OK. Now, within pressure anchoring, we have the option of anchoring the pressure with an average pressure or a particular cell pressure. We will choose a particular cell pressure. Now, once again, we want to select a cell that's away from the interface between the two phases. So we will choose one that's clearly within the gaseous region. To identify this cell, we will go to the Tools pull-down menu, go to Problem Setup, and XYZ location to cell number. And here we will specify the following location: minus 0.125 in X, 0.055 in Y, and 0 in Z. Once this has been entered, we will save the input file and then write and run in the tool runner. This particular location has 4 cells that are close to it. We can choose any one of these. For this case, we will just choose the last one, cell number 9850. So we can remember this number, press OK, and then dismiss to exit this tool. We will keep the reference pressure value at 0, and for the cell number to anchor, we will choose that 9850 that we got from the XYZ to cell number tool. Once this has been entered, we can press OK to confirm and proceed. For the initial conditions, we will be initializing using XYZ boxes. We will create one XYZ box information set. We will highlight this XYZ box information set and check it. Within this, we will apply 2 different XYZ boxes. So we will add one more. For the first XYZ box, which we'll highlight with a single left mouse click, we will keep the default domain extents, which encompasses the entire computational domain. For the initial conditions for this box, which will be for the gaseous phase, we will add one information set. We will highlight this information set while also checking it. For the static pressure, we will enter 0.0. This is relative to the base pressure value that we've applied in the fluid properties panel, which was 1 atmosphere. The velocity values we'll keep at 0. The turbulence quantities we will initialize at a later stage. Since this is the gaseous phase, which is the hidden phase, we will apply a volume fraction of 0.0 to the tracked H2O liquid species. Next, we will highlight the second XYZ box information set. This will be the initialization for just the liquid phase. So we'll enter a Ymax of minus 0.042. Hitting apply will show you the new domain extents of this XYZ box. The Ymax location will be the interface between the 2 phases. The information set for this box, we will need to create a new one. So we will add a new primitive variable information set. We will highlight this while also checking it. The static pressure will be set to 0.0, which is relative to the base pressure, so it's 1 atmosphere. The velocities will be kept at their default values of 0.0 meters per second. The turbulence quantities will be kept at their default state for now. We will initialize them at a later stage. And since this is the initialization for the liquid phase, we will enter a volume fraction of 1.0 for the H2O species. Once this is done, we can press OK at the bottom to proceed. Next, in the boundary conditions action panel, you'll notice that all of our boundaries created by the cutting and blanking controls have automatically been set to be overset patched without offset zonal boundary conditions in these boundary families. We can leave them with these boundary conditions and just apply the boundary conditions for our other boundary families. All other boundary families in this particular problem can be set to be viscous wall boundaries. Next, we will apply boundary conditions to the other boundary families. We will first highlight left using a single left mouse click. Then we will hold down the control button and highlight right, bottom, top, and ball. All of these boundary families will be set to be wall boundaries, so we can hold down the left mouse button and drag and drop into the wall boundary conditions tree. Here we will apply a viscous wall using wall functions. Everything will be stationary with respect to mesh motion. No modifier will be applied, so we can keep these unchecked. And once this is set, we can press OK to proceed. Lastly, we have the zonal boundary family for the overset ball. Here we will single left mouse click to highlight it, hold down the left mouse button, and drag and drop into the zonal boundary conditions tree. For the zonal connection type, we will apply patched and overset. We will not be applying any sort of offset. We do not need an alternate boundary condition for this zonal BC. And the interface condition to be applied will be a simple flow through. All other options can be left unchecked, and we can press OK to confirm and proceed. Now, if you go to the notebook and hover the mouse cursor over each boundary family, you'll notice that details of the boundary conditions applied will be given. And you will also notice a green check mark next to each boundary family. This signifies that a boundary condition has been applied to this boundary condition. Otherwise, a red X mark will be visible, indicating that a boundary condition needs to be applied. Once all of this is set, we can press OK to confirm and proceed. Next, we're taken to the zonal connectivity options panel. We can leave everything in its default state for this example and press OK to proceed. In the grid motion specifications action panel, we will want to apply a grid motion to the overset grid. we apply grid motion to specific cell groups. So if we go to the groups tree in the notebook, we can identify that the group number 2 is the overset grid. So we will highlight this using a single left mouse click. The grid motion that we're going to apply to this group will be an analytic translation or rotation velocity grid motion. So after highlighting this group with a single left mouse click, we will hold down the left mouse button and drag and drop into this particular grid motion type. So we will want to apply a translational motion in the y direction. So we will apply minus 4.0 meters per second. We'll press OK to proceed. Once this is set, we can press OK to confirm and proceed. Next, we're taken to the overall grid motion control panel. We want to turn on the defined velocities, which is already marked as yes. We want to physically move the grid with the selected velocities, so this has been marked with yes as well. We want to recalculate the zonal connections at each time step. That's been marked as yes as well. So we can keep these settings and press OK to proceed. We can also keep the default settings in the turbulence control action panel. Next, we are taken to the turbulence initialization tool panel. We will highlight the first information set with a single left mouse click. This information set is for the gaseous initial conditions. We will hit the right mouse button to bring up the turbulence initialization calculator. We will keep the option for is the turbulent length scale known to yes. For the free stream turbulence level, we will keep the default 3e-2. And for the length scale, we will keep the default 0.01 meters. For this free stream velocity, we will enter 4 and we will compute. This will then prompt us with the panel showing us the computed K and epsilon values as well as the estimated mu-t over mu ratio. We'll press OK to this and press OK to confirm this. Next, we will copy these values to the other information set. So we will choose the information set source, the one we just computed the turbulence values for. And the destination will be the other information set, which was for the initial conditions for the liquid water. We will press apply and then press OK. And you will see that the K and epsilon values have been copied over from one information set to the other. Once this is done, we can press OK to proceed. We will not be using the help set numerics wizard for this setup, so we will keep these options as no and then proceed. The Riemann solver panel can be kept in its default state. In the simulation strategy action panel, we will say no to the option for is this a restart since we are starting from scratch. The number of global steps for this run will be set to 1,000. Then we'll press OK to proceed. Then we're prompted with whether or not we want to load some default settings for the transient mode. We will say no to this option and press OK. For the global time step size, we will say user given. In the current number for the local time step ramping, we will keep the default settings. For the global time step size, we will enter 2e-5 seconds. And we will enter the number of iterations as 100, allowing it to terminate only once it's reached a 1e-5 drop in residuals. The order of global time stepping we will keep at the default first order. For the coupled solver variable under relaxation, we will enter 0.375. Once this is done, we can press OK to proceed. In the spatial discretization action panel, we will expand the advanced controls. The one additional change we will make here is to turn on the artificial compression. This will help sharpen the interface between the two different phases. Once this is done, we can press OK to proceed. In the neutral plot file options panel, we will keep the default outputs and press OK. We are then prompted with whether or not we want to write out the neutral plot file options input file based on these output options. We will keep that as checked. We will also copy the neutral plot file options input file to the plot output options input file. So we'll press OK. Next, in the probe and output files action panel, we will check the option to output the neutral plot file with step appended. Since this is a transient computation, we want to output the solution. Since this is a transient computation, we want to track the solution by outputting it at specific intervals. By outputting a step-appended neutral plot file, we can then create an animation of the simulation. We will enter a frequency of output as 20 steps, so every 20 steps a step-appended neutral plot file will be output. Once this has been set, we'll press OK to proceed. Now we're ready to save the input file and run the simulation. We will do so in double precision mode using a single CPU. All output files will be written to the current working directory. For more information about post-processing and visualization, please refer to the post-processing section of this example. Thank you.